All right, the next talk is by Karnbongkot Boonriong, who will, sorry for that, who will present her master thesis at Imperial College London.
Hello. Okay, great. So we'll be looking at randomized testing of the Dafny compiler in the CI. I know that's a lot of words I just said, but basically randomized testing or fuzzing is a software testing practice where you generate a bunch of random input and you would put them into the software under test, and maybe one of the input will produce an unexpected output, and then you would know that you found a bug. And when I say in the CI, I meant continuous integration, which is a practice where code changes are integrated frequently, and this often involves automated building and testing. This is the case for the Dafny compiler. So a tool that does fuzzing is called a fuzzer, and in this work, we'll be using a fuzzer called fuzz-d. This is work done by a student from Imperial College London, Ali, my supervisor, and John Tristan from AWS. I'll tell you a little bit how fuzz-d works and how the type of bugs that it can find in the Dafny compiler. So fuzz-d always starts with generating a well-defined Dafny program. It will then try to pass that to the Dafny compiler. And at this point, we have an opportunity to find one type of bug, and that is called the compiler crash bug. So given a valid program, the Dafny compiler would just terminate without producing any valid output. It might come with error messages like that. If we find that, we would keep that test program, put it in a pile somewhere, and then we'll start again by generating another program in hope of finding more bugs. If that doesn't happen, we'll try to compile Dafny into all of the supported languages, try to compile the resulting file using their respective compiler. At this point, we can find another type of bug, which is called the non-compliant code generation bug. And this happens with Dafny more than with other languages because Dafny compiles to high-level languages, so these have a lot of rules and stuff. And this happens when the Dafny compiler emits code that doesn't comply with the rule of the target language, so it would just fail at the target language compiler. If that doesn't happen, we'll try to execute all of them in parallel. And here we can find the last type of bug, which is called the miscompilation bug. This is kind of like the most dangerous type of bug because it doesn't produce any errors. It's just silent all the way through until the end. And the only way you can find out if this type of bug exists is if you compile them to multiple languages at once and compare it. Yeah. So why do we give a fuzz? So imagine this is the execution tree of the Dafny compiler. Dafny already have a lot of regression tests in the CI that covers a lot of the branches in this tree. But as you can see, there might be some edge cases that is not covered using regression tests. For some type of software, this could be fine. It could be forgivable to have edge case bugs. But for Dafny, this could mean that in some of these edge, there might be miscompilation bug there. So that means that provably correct code might be compiled wrong and then behave incorrectly. So we're basically giving false guarantee to the user. And fuzzing is actually good at getting into these edge cases because it uses a lot of randomness. So together with regression tests and fuzzing, we have more chance of catching all the bugs and covering most of the execution tree. But then fuzzing and finding a program that trigger a bug is only the first part of the compiler fuzzing campaign. You still have to deduplicate the bug, which is the process where you find out if the bug that you found is actually a duplicate of something that's already known, already reported. So you need to eliminate that. You also need to reduce the test program that trigger a bug. So usually the test program would be really, really long. And you need to chop away all the irrelevant part of it until you have only the smallest part that still trigger a bug. You might need to bisect the bug in order to find out which commit in the history of Dafny compiler actually introduced the bug. Then you just have to report it and maybe monitor it to see how the developer are getting on with the bug. So only fuzzing is automated, well, before this work, and everything else was manual. And it takes quite a lot of effort to go and do all of that. And as a result, we have, like very, very powerful fuzzer that can find a lot of bugs, but then nobody ever uses it because they don't have the time to manage a fuzzing campaign. And that means that we have a project timeline that looks like this. So over time, bugs kept getting introduced. At some point, somebody comes along because they finally found time, and they do a huge fuzzing campaign that discover all of the bugs in the past. But then by that point, maybe the context of the bug is already lost, or even worse, maybe there will be other features that build on top of the code that contains bug. So then if you fix the bug, it will have bad consequences. So then we ask ourselves, okay, what about we do a mini fuzzing campaign as part of the compiler CI? So instead of a timeline that looks like this, we can have something that looks like this. So hopefully with smaller amount of fuzzing, we might be able to find these edge case bugs and fix them while the context is still fresh and nothing else is built on top of it. Long story short, we automated all of the steps that you've seen before. I won't get into the details, but I'll be happy to talk about it after, about how we implemented that. So we containerized all of these things, and every time somebody opens a pull request in the Dafny repository, that would trigger the tool to be deployed and run, and then it would just report bugs back to the Dafny developer, either with pull request comment or as a GitHub issue. Yeah, and I think the tool was quite successful. It has found 3 previously unknown bugs between August to September. But I think what's even cooler is that we learned a lot of things that was not known before. For example, this is something that we've learned from fuzzing Dafny to Rust, which is the previous talk. Because the Dafny to Rust, the Rust backend was being kind of actively under development while the tool was deployed, we run into a lot of issues where the tool wasn't able to tell if an error it's getting is from the feature being unsupported or it has found a bug. So for example, we have this error from when the Dafny compiler, the Rust backend crashed. And as human, you can kind of read and see that it's about unsupport invalid operation. But the tool didn't know. So we reported it, turns out it's not a bug, and we decided to ignore all of the errors with the same class. So that was kind of easy. But then we run into other more complicated case. So in this case, we have a code, a Dafny code. It compiles successfully into Rust, but then when you feed the Rust code to the Rust compiler, it comes out with this error. And once again, this was actually not a real bug, and it's because the Dafny code contain traits that has constant attribute. And during the time that we were testing this, constant attribute on trait was not supported, even though trait was already being implemented. So as human, I don't think we'll be able to tell if this is a bug or it's just unsupported. And the only people who would know is Mikel or Fabio. So this is actually still unresolved, and I think there will be more cases like this. But it does raise the question of, when is it the right time to start fuzzing a compiler? Because on the plus side, you know that if bugs can be found early, they can be fixed early. And as Ali found in his other work, fuzzing can also kind of prevent developer from committing to a problematic implementation or design. But then as we've seen in this work, the fuzzer catches a lot of the unsupported features, and it cannot tell if it's a bug or not. They report it to the developers, and that's kind of annoying, and it's a waste of resources, to be honest. Okay. We also learn a lot of things from trying to automate bisection. So if you're not familiar, bisection is actually a process of trying to find the commit that introduced the bug. And you do this by searching in the history of change of the Dafny compiler in a binary search fashion. So every step of the binary search, you would kind of check out the compiler at that version, build it, and then test it. So if the bug exists or doesn't exist, you just kind of follow the algorithm until at some point you find the first commit where the bug exists. And this would require you to invoke the Dafny compiler in an equivalent manner, like wherever you're in that history. And this turns out to be pretty hard because things change a lot over time. So there were changes to the command line interface, right? You have the new command line now. The old one is getting deprecated. But then at some point, if you're bisecting back in time to when the new command line doesn't exist, you need to invoke the old command line in the way that would produce the same output as the new one. So that's one thing. There are also changes to the compiler default flag values. So at some point, maybe warnings in the compiler would be treated as error, and at another point, it is not. So you need to know exactly where that point of change is so that you can know, okay, after this version of Dafny, I need to expect errors to rise from warnings or just start suppressing. There are also changes to the interaction between the Dafny compiler and the downstream tools. So at one point, maybe the Dafny compiler so when you try to translate Dafny to Java, maybe at some point it would invoke javac to produce class file. At another point, it would invoke javac to produce jar file. And because we need to execute the resulting file, we need to know which type of file we're actually dealing with. There were also temporary breakages, which is normal. There are also changes to the dependencies in the compiler. But I think the point of this is, for compiler developers to kind of be more cautious about the changes you're making, either with the user interface or anything else, in order for automated bisection to work a long time. Because I think Dafny is relatively young, and even that, there's already a lot of obstacle in doing automated bisection. We also run a simulation to figure out if CI fuzzing would have been helpful in the past in finding bugs. So we did simulation with 20 known bugs that was introduced by 13 pull requests. So out of the 10 repetition that we've done, 6 of the 20 bugs were always found. And there were 14 that were just never found. So now let's look a little bit into why. 8 of the 20 bugs were actually missed because of the fuzzers limitation. So in this case, it would be fuzz-d limitation. So for example, it might be because the keyword that is required to trigger the bug is way too specific for the fuzzer to generate. Or maybe the bug is related to recursion, and most fuzzers aren't able to deal with recursion. But I think this would inspire anyone who's trying to make a compiler fuzzer for any compiler to kind of look into how the compiler works internally and think about where its weak point might be. Because for Dafny, because you're compiling into a bunch of other high-level languages, you will need to escape the keyword in those languages properly. So maybe when you make a fuzzer, you can say that, okay, whenever you generate a test file, try to include some of these keywords. So you can check if the Dafny compiler is escaping it properly or not. 6 of the 20 bugs were missed because of complexity. And this is actually interesting because it was found during a 12-hour fuzzing campaign, but it was missed in the 2-hour fuzzing campaign. But I think this is to show that the mini fuzzing campaign is not good enough as a replacement to a longer one. Therefore, we should still keep the longer fuzzing campaign, working somewhere. Maybe as like a nightly fuzzing. So we would have nightly fuzzing, and then we would have like fuzzing in the CI. So yeah, to conclude, I think compiler fuzzing in the CI can be really helpful in catching edge case bugs during development. It should be applied as a complement to regression testing and as complement to nightly fuzzing as well. Fuzzing early is not always the best thing to do, especially when you have things that are not completely developed yet. For automated bisection to work long term, the developer should be mindful about changes or maybe maintain a backward compatible interface. And for people who are trying to make fuzzers, in addition to generating interesting programs, you might also figure out how to exploit the compiler's weak point. Okay, thank you.
Yeah, so I'm curious about what the process of, so you have your random program, you want to find the part of it that generates the bug. I'm curious what the process of finding that looks like. I don't quite remember the term you used for it. But are you essentially just kind of pulling out random parts of the program and ensuring that it still should compile and then seeing if it causes the bug?
Yeah, so that is a process called reduction. I'm not sure how much detail I should get into here. But imagine you have the AST of the program, of the test program, right? You can kind of prune part of it, like just cut part of it out. And then you have like a smaller size program. Then you would try to run that program again, see that it compiles, see that it still triggers the same bug. Then you would know that, okay, this is a good version of the program. Another case can also happen that when you take out some part of the program, it doesn't trigger a bug anymore, or maybe it doesn't even compile. Then that would be a bad version of the reduced program. So you would do this repeatedly until you get the smallest size program that still triggered a bug. I'm not sure if is that good?
Yeah.
So you mentioned this 12-hour run compared to 2-hour run, didn't find it. Are these runs stateful? Because, I mean, if you're running these things on every commit of CI, then surely you can get 6 2-hour runs that would be equivalent in, I don't know, bug finding power.
Yeah. So these things are pretty non-deterministic because, again, it's just randomly generating program. And if you go back here, for example, the first program has like 3 things that are required to trigger a bug. And you were just relying on luck that the fuzzer would generate all those 3 things so that it can trigger a bug.
But you could still, like, with 2-hour campaigns, you could still accomplish the same.
We can if we're lucky.
Okay. I guess this is maybe more of a comment, but like you mentioned unsupported operations being indistinguishable from failures and like whether, you know, this would be a bug. I would say that that was obviously a bug in the sense that, you know, a portion of the code that's not finished should have markers saying it's not finished. And if it doesn't, then that should be reported as something
Yeah,
fixed.
it is a bug in the theoretical sense, but then I think we want to be helpful to the developers, so we want to.
Well, and you also want those unsupported operations to specifically be written in a way such that your CI can pick them up reliably.
Well, I think it's already kind of obvious. At least, like in this case, it was easy to avoid, right? But then I think something like this might be a little bit harder to do. I'm not sure.
Well, I mean, this looks like it managed to get past the part where it should have reported unsupported.
Yeah,
and
but
it went up through the Rust compiler and then it started complaining.
Yeah, I think it would just put more burden on the developer who has to mark things, so like to check that, okay, if there's no constant on trait, if there's constant on trait, I shouldn't do errors. So yeah.
Let's thank Wu again.